My name is Mihir, and this is my project called the Thermodynamic Model of the Respiratory System in COVID-19 effects. So in the interest of time, I'll get back to this slide a bit later. So basically, what I did was, in order to analyze the disease of COVID-19, which was quite a recent pandemic, I created a model of the respiratory system in terms of the laws of physics and use it to analyze its symptoms. So basically, how I did it is I based the idea around the concept of physical efficiency. So what I did is first I isolated a component of the respiratory system, found a suitable method to evaluate its efficiency, parameterized solely by macroscopic thermodynamic variables, so pressure, volume, temperature, etc. And then I calculate the efficiency under healthy conditions. Then in order to analyze the symptom, I reparameterize, recalculate the efficiency, and then using the comparison, I made predictions of the effects. And so in my paper that I published, I analyzed these three respiratory components, and the symptoms I chose were fever and pneumonia, mainly because they have very well-known effects. So they're a good test to see if the model works. So the first component was lungs and the breathing mechanism. In order to parameterize this, I modeled the lungs as a heat engine. This is because when I graph the pressure volume curve, which is here on the right, it largely resembles a two-stroke heat engine. This is because a heat engine works as per this diagram on the left. It supplies heat, some of which is transferred into useful work. The rest is expelled as useless heat. And if you think about it, the lungs work in a very similar fashion. You breathe in some air, some is used in respiration, the rest you breathe out. And this means that a suitable efficiency measure could be engine efficiency. But what actually is engine efficiency? Well, when you're talking about a heat engine, there are two main efficiencies you speak about. Cyclical, which is really just the ratio of work to heat input, and Carnot. For cyclical, the work done can be calculated by this expression, the heat, by these two not nice looking ones, but they're both really just conservation of energy statements. And putting them together gives a cyclical efficiency under healthy conditions to be 3.25%. Now, as for Carnot efficiency, it's a little bit more complicated. What a Carnot efficiency is, it's basically an efficiency of something called a Carnot engine in the same environment. And a Carnot engine is basically a theoretical ideal heat engine, the efficiency of which depends only on temperature. And so you need to determine what the hot and cold reservoir are. If you say the hot reservoir is the body at about 310 Kelvin, and the cold reservoir is the surroundings, if room temperature is about 296, you get a 4.5% Carnot efficiency. And with these two efficiencies, you can represent the lung engine under healthy conditions and reparameterize for symptom analysis. For example, fever. Fever is temperature-based, means Carnot efficiency is probably a better tool. If we say fever temperature is 312 Kelvin, a 2-degree Kelvin increase, you see a 0.6% increase in Carnot efficiency, which shows that lung efficiency increases with fever, and that tracks with the fact that you experience an increased lung function to support immune responses such as phagocytosis and antibody production. Pneumonia, on the other hand, is pressure volume based, which means cyclical efficiency is more appropriate. In this case, you don't actually need to make calculations because when fluid fills up in the lungs for pneumonia, the maximum lung volume is restricted, and so the gas cannot expand as much. This means it does less work, and so cyclical efficiency itself would reduce, which is another common symptom of pneumonia. The next component was diffusion and gas exchange. In this case, the efficiency is a lot easier to find. It can just be the rate of diffusion, and that can be found by Fick's law, which shows that the rate of diffusion is equal to the diffusion coefficient times the surface area times the pressure gradient. It also gives us this quantity called diffusional resistance, which you can interpret physically as how hard it physically is to breathe. Because with a higher diffusional resistance, going to Fick's law, you need a higher pressure gradient for the same diffusion rate. And so you quite literally have more labored breaths. Now, another good thing about this equation is because the whole efficiency depends on that one equation with standard quantities, you don't actually need a healthy efficiency. You can express infective efficiencies in terms of the healthy efficiency. So for example, in fever, if we say dN over dt1 is healthy and dN over dt2 is under fever, you can use gas laws to find the variations of Fick's laws quantities to show that there's a 1.3% increase according to this model in fever, which once again tracks with the fact that there is increased lung function during fever. As for pneumonia, because of the uncertainty you have during fluid fill, it's very difficult to obtain data pertaining to said fluid fill. but you can still determine an effect simply by manipulating the algebra of Fick's law. As you can see here, Fick's law shows that the rate of diffusion is proportional to the ratio of surface area to membrane thickness, and the diffusional resistance is inversely proportional. Now, because fluid fills up in the alveoli, the thickness effectively increases as the oxygen has to diffuse through the fluid as well, and the surface area will decrease. This decreases this ratio, and so the diffusion rate itself will decrease. The resistance, on the other hand, will increase, and as we said before, this will make you experience more labored breaths, which is a common symptom of pneumonia and evidence that this part of the model predicts accurate results. And so the final component that I analyzed was respiration and oxygen uptake. Again, this is a fairly straightforward efficiency measure. If we just use the rate of respiration, we can use something called differential rate law to calculate this. A differential rate law, however, requires the knowledge of the blood concentration of oxygen. Since we're only interested in the concentration of oxygen and not quite what happens to the oxygen, if we approximate the blood uptake of oxygen as gas dissolving in a liquid, we can negate the reaction between hemoglobin and oxygen, because this eventually reverses when it's absorbed for respiration. And so that allows us to use something called Henry's law, which is an equation that relates the concentration of a dissolved gas to the partial pressure. And that's a quantity we have from earlier. That gives us an accessible efficiency measure that can be reparameterized. And it's important to note that because of this, the change in the rate of respiration depends more on the rate constant in the differential rate law and oxygen concentration, because Henry's constant has a very negligible change. And the variation of the rate constant is found in Arrhenius' law, and the oxygen varies as per Henry's law. Putting these together, you can find that there's a 17.2% increase in the rate of respiration. And this, again, further implies the increased lung function, as a higher energy production rate is better for a more effective immune response. Pneumonia, once again, because of the difficulty to obtain data for, we have to use the same technique as in the previous section to find the effects. Say, because from the previous section, we know that there's a lower rate of diffusion, and it follows logically that there is a lower blood oxygen concentration, and so according to differential rate law, it says there's a lower rate of respiration. Now, logically, this would lead to effects such as fatigue and loss of appetite if you have a lower energy production rate. And again, both of these are characteristic of pneumonia patients. So that is evidence that this section of the model predicts correctly as well. So overall, all the effects derived by the model appear to be consistent with the known effects of fever and pneumonia. This model seems to have some clear advantages and disadvantages as well. It can produce accurate qualitative results. It's preferable to experimental technique in terms of cost and time, and it can be used with insufficient data by mathematical and algebraic manipulation, which is what we did with pneumonia. It got one main flaw, which is that it can't produce accurate quantitative results, because the amount of idealization and approximation that you require simply to bring this biological system into a math model is far too much, because obviously not everything is modeled mathematically. But overall, I do believe this model has the potential to be a useful tool in medical research, as it can be used when researching respiratory diseases to uncover unknown effects in the cardiorespiratory system. It can even be useful in guiding experimental research into testing potential effects predicted by the model, which will ultimately save time and money in medical research, which I believe would be the main reason behind using this model. And yeah, that's it for me. Thank you all so much. Before we go to Q&A, I'd like to thank my mentor Quantum for all his help every step of the way, and of course the Polygence team for this fantastic opportunity.
Thank you so much, Mihir. Great, so let's start with the questions that are in the Q&A from Jen. She's asking that, she's saying this is such a novel way of thinking about COVID symptoms. What gave you the idea to kind of use physics and geometry and math as a lens to analyze COVID in this way?
Well, it actually came to me when I had COVID and I had my physics exam the next day. I found it difficult to read my book, and then I was thinking maybe I can use this physics to help me and other COVID patients one day.
Connection. other Q&A question. When conducting your research, what did you find the hardest aspect, and what would you perhaps do differently?
The hardest aspect was, well, it was mostly finding data about pneumonia, because it's such an kind of uncertain effect. It's very difficult to find the data required for. So I'd say the hardest part was finding a way around that using like the technique of algebraic manipulation. Apart from that, yeah, it was just kind of, it was hard thinking to tackle every system differently.
Great. The reviewer question is, based off what you know about COVID-19, are there any other possible symptoms outside of fever and pneumonia that may be relevant to your model?
I believe that anything to do with coughs or sneezing would be quite relevant, because they're very like instantaneous style reactions. So it would be, I feel like it's an interesting application of this model to kind of see the spontaneous effects on macroscopic thermodynamic variables of these things, and perhaps they could be quite useful at determining extra effects.
Awesome. Great job. Thank you so much.